So we're going to go ahead and review some important concepts here related to waves in preparation for our test here on waves. So we'll start with just the basic parts of a wave. Up first we have the amplitude. So amplitude is the height or intensity of the wave measured from the equilibrium position. As a refresher, the equilibrium position is just the middle of the wave. So our amplitude here would be either this distance from the equilibrium up to a peak or crest, or this distance here from the equilibrium down to a valley or trough. We typically abbreviate amplitude as just a capital A. It's oftentimes measured in meters, but it doesn't necessarily have to be. For like waves in an ocean, it would be meters, but for some other waves, it might be another measurement because it could also be just the intensity of the wave. Up next, we have wavelength. That is the length of one full wave. So for that, we can measure from valley to valley or trough to trough. We can measure from peak to peak, or we can go somewhere in between to the point where the wave begins repeating itself. Wavelength, we use the Greek letter lambda to measure it. So these are all the wavelengths, which is lambda, kind of like an upside down Y. And the units for wavelength are going to be meters. So that one does have a fixed unit. Up next, we have the period. Period is the time for one full wave. We usually abbreviate it with a capital T. Anytime we have repetitive motion, we often talk about the period, and the period is always going to be the time for one full motion. So the period is measured in seconds. All right, that is our standard unit for it. And then lastly, we have the frequency, which is just an F. Frequency is the number of waves per second. It is the inverse of the period. It's measured in hertz. And keep in mind that we do have this equation that links period and frequency, and that is that the frequency is just 1 over the period. We also can say, and it's just a matter of rearranging this equation, that period is 1 over the frequency. So that kind of works both ways. Next, we have the two types of waves. The first is a transverse wave, and this is what we typically think about when we think of a wave. The key is that waving motion is perpendicular to the motion of the wave. So the wave itself, the velocity of it is traveling to the right, okay, while the wave is waving up and down. All right. The second kind is a longitudinal wave. I always remember that the wave goes along with the velocity, so in that case, the waving motion is parallel. I think the easiest way to think about this is with a slinky. So if you imagine a slinky, we're going to have some spots where it's really close together, and then spread out, and then close together, and then spread out. So it's these pulses basically that travel along. So the wave is going that way, and the waving motion is parallel, going back and forth. All right, so let's next talk about the velocity of a wave. And so we'll start with the formula that we've looked at before for the velocity of a wave, which is that the velocity is equal to the wavelength times the frequency. So this v, of course, is the velocity in meters per second. Lambda is the wavelength, and then f, of course, is going to be the frequency. So looking at that equation from before, you might be tempted to think that, well, changing the wavelength or changing the frequency will ultimately change the velocity of the wave. But actually, neither one of those is true. There's only one way to change the velocity of the wave, and that is to change the medium. You have to change something about what the wave is traveling through. Whether it's, if it's traveling through air, you have to change the temperature of the air, change the humidity. If it's on a string, you have to change the tension of the string or something like that. But it has to be something about the medium and not the wave itself in order to change the velocity. And you might look at the equation and say, well, if we increase wavelength, that should change it. But what will actually happen is if the wavelength goes up, frequency will go down to maintain the same velocity, and vice versa. The only way to change it is to change the medium. We're now going to talk about what I refer to as the Shunn words, which are the different properties of waves. Okay, and these are things that any wave can exhibit, and we certainly can look at examples of them in different types of wave, whether it's sound waves, waves on a string, waves in an ocean, light waves. But we're just going to talk about these properties in general and what they mean. So the first property is superposition, and this is the ability of two waves to combine to form a bigger wave, a smaller wave, or just a more complex wave. Okay, so two waves can come together and they basically create a new wave that's a combination of those two. We talk specifically about constructive interference and destructive interference. And so constructive interference occurs when the two waves come together to create a bigger wave. Destructive interference occurs when the two waves come together and either fully or partially cancel each other out. But all these are examples of superposition, the waves coming together to form a new wave. The next one we talked about was diffraction, and so diffraction occurs when we have an opening, and so a wave might be coming up to that opening, and what's going to end up happening is it's going to spread out as it goes through that opening. All right, it doesn't just get blocked and confined to the area directly in front of where the opening is. Waves have this natural tendency to spread out when they go through openings. The next one is reflection, okay? And so this is the ability of a wave to bounce off of a surface and change directions. We see this most commonly with a light wave. So the wave comes in here, hits the surface, and then it's going to reflect off like that. If we get into the optics unit, we'll talk a little bit more about this, but the angle it goes in at and the angle it leaves at are actually the same, but we don't need to know that for now. We just need to know that reflection is this property of waves bouncing off of a surface and traveling in the opposite direction that they were initially going. And the last property we have is refraction, and this occurs when waves travel from one medium to another. Something changes about the medium, and what happens in turn is the velocity of the wave changes, and it leads to the wave bending. So we might have a situation where the wave has a high velocity in one section and a low velocity in another, and so what ends up happening is the wave comes in, okay, and when it hits this surface, it's going to bend. So it might come in like that, and then it would bend like that. And so what we see is the direction that the wave is traveling changes when it crosses that boundary, and the medium changes, ultimately changing the velocity. So that's what refraction is the bending of a wave when it goes from one medium to another. So moving on, let's talk a bit about the basic properties of sound waves. I just want to identify two common things within sound waves and how they relate to the wave itself. So the first is pitch. The pitch of a sound wave really depends on the frequency of that wave. That's really when we're talking about pitch, it's really the frequency that we're thinking about. Higher pitch means a higher frequency. And then the second property is volume, and the volume of a sound wave depends on the amplitude of the wave itself. So more volume corresponds to a higher amplitude for our sound waves. So one of the next things we talked about with sound waves was the idea of standing waves within an instrument. And just as a refresher, standing waves are situations where the wave is kind of fixed in place, as you see in the animation. We have these points here that we refer to as nodes, where the wave is not moving at all. And so when we're dealing with an instrument that's playing a note, what's really happening is a standing wave is being created within that instrument, and the frequency of that standing wave is what we ultimately hear. So there's two broad categories we're going to talk about, and these would apply to either waves that are on an oscillating string, like with a guitar, violin, etc., or waves that are in a column of air, like a flute, clarinet, something like that. And so the first case is when we have a situation where it's either what we call open-open or closed, but basically the two ends of the string or column of air act the same way. And when we have that scenario, the equation we're going to use is L equals m lambda over 2. So in this case, the L is the length of the string or pipe. Lambda, of course, is our wavelength. And then m is going to represent what's called the harmonic number. And it can either be 1, 2, 3, so on. And the whole reason why we have that harmonic number there is for any given length, and we'll talk about this more in a second, there's multiple waves that can create standing waves within that space. All right. And so you're going to see that there are going to be multiple frequencies, multiple harmonics that will have for any given wave, or for any given length of string or length of column of air. So that's what happens when it is either open open or close close. The other option we have is when one end is open and the other end is closed. In other words, the two ends are different. And that would be this case here, the open-close situation. And when that is the case, our formula becomes L equals m lambda over 4 now. So obviously m and lambda represent the same thing. The one difference, though, is now m only represents the odd numbers, okay? And that's just the nature of an open-closed standing wave. All right, and so we see over here, like I said, the examples of what they physically look like, fixed in time, oscillating between these two states for open-open and for open-close. So let's talk for a second about harmonics. We kind of see examples of this here, and we also see a very clear example of the first 4 harmonics for a given string. And basically, harmonics are just the idea that for any given length of string or length of pipe, we can have multiple different wavelengths that will exhibit standing waves within that string or pipe. And we call these different wavelengths different harmonics. A few important things to note with harmonics. When you ultimately hear a note, the fundamental frequency is the one that you actually are hearing, which represents the first harmonic. So that's one important piece to this. A second important thing is that for open-open, we have all the harmonics, but for open-closed, we only have the odd ones. And that's reflected here in the fact that this formula only includes 1, 3, 5, etc. The final thing that's important is when a note is played, all these different harmonics undergo that combination that we talked about before, superposition. Okay, so they all superimpose, and they end up creating a more complex wave that has a richer sound quality to it. And so that's what we end up hearing. The frequency is the fundamental frequency, and that's the pitch we would say it is, but these additional harmonics help to add to the richness and complexity of the sound. The last topic we have to talk about within the waves unit is the Doppler effect. So we'll start for a second by talking about it conceptually, and then we'll get into the math. So conceptually, the Doppler effect, what it is it's the apparent shift in frequency caused by motion between the source and the observer of a sound. So basically, if you have either the source of a sound moving or the observer of that sound moving, what's going to end up happening is the observer of the sound, the person hearing the sound or the thing hearing the sound, is going to observe a different frequency than the one that's actually emitted from the thing making the sound or the source. Okay. Mathematically, we do have a formula that allows us to calculate this shift. And so what that formula says is the frequency observed, FO, is going to be equal to the frequency of the source times V plus or minus VO over V plus or minus VS. So we'll talk about the plus or minus piece in a second, but let's first define these variables. So FO and FS are the frequency, in this case, the frequency of the source or the frequency of the observer of that source. VO and VS are going to be the velocity, again, of the source or of the observer of the source. And V is going to be the velocity of sound, all right, which we know in air at a reasonable temperature and humidity. Technically, it's 20 degrees Celsius. We know that this has a value here of 343 meters per second. And unless you're told otherwise, it's safe to assume that that's the V you're going to use, these guys right here. So let's talk about the plus or minus piece. So when the objects are moving away, either the observer is moving away from the source or vice versa, two important things here. Number one, that leads to the frequency decreasing. Okay, so when there is motion away, frequency decreases. And what happens equation-wise is we would say the frequency observed is the frequency of the source. And in order to get that decrease to occur, we're going to subtract on the top of that fraction and add on the bottom. Okay. Now, I always kind of reason my way through it, but certainly you can just use this as a guide to work through, and just remember that it's minus on top, plus on bottom for motion away. And when motion is towards, what that ends up doing is It means that the frequency increases. And when the frequency increases, mathematically what we're going to do is we're going to say FO equals FS, and then we're going to add on top and subtract on the bottom, because both of those mathematical operations will lead to a bigger observed frequency than the source. We want a bigger number on top and a smaller number on the bottom.